Oh, yeah. Absolutely. Oh, this is getting great. What did I do? I think it's going to help you. This is just display. It's going to be epic today. Epic.
And it was right after spring break. It was like, I'm recharged, and I'm back, and then...
Uh-oh. Okay, welcome. EE123, lecture 26. Woo! Huh? Didn't fall. Okay, today's my favorite lecture. It truly is. It's what I've been doing actually for almost 12 years now. So I should know something about that. Before this, I want to briefly talk about Lab 4. A few tips that I posted on Piazza. Make sure you have good signal, like the one that I recorded. Okay, the spectrum should look like this. You should see the TDMA frame. If you don't see the TDMA frame, it means that your SNR is not very good. Okay, that's basically what it means. It means that your noise floor is quite high, so you don't see the dips. Okay, so really important that you get a good signal. The other thing is that you should see, if you look at the spectrogram, you should see the bursts really nicely. It's the same way as you do with the data I gave you. Okay? And there's plenty of places around campus to do this, even in this classroom. So I gave you many, many options of GSM base stations around here. One thing to do, here's just an example. Oh, I've got a Fluke here. But this is, as you can see here, this is kind of the drift that happens as the temperature increases in this device. And so over time, when it heats up, the frequency offset goes up. This is kind of a fluke that happens. I guess somebody entered the door, the reception was gone. Something like that, maybe. But if you do, after you let it heat a little bit, if you go like this, so I cooled it a little bit. by putting cold air through it. So you can see actually how it immediately dips down. Now some of yours don't have as many holes in the ventilation. It depends on the dongle that you have. So it might not react as fast. But again, if you put something cold next to it, you blow air on it, you'll see that actually temperature will go down, and then your frequency offset is going to go down. And then it's going to start building up again as it gets hot. It's pretty cool. It's kind of like a temperature sensor if you think about it. Yeah, I guess you can calibrate a temperature sensor on this one. Absolutely. Okay. So the other thing that I want to mention is that pay attention for the burst detection code that you are writing. Exploit a lot of things, also not necessarily just the threshold. You know what the length of each burst should be in samples. You know how far they should be from respect to each other. At least 5 bursts are at same distance, and then the 5th burst is a little bit off within a frame, a control channel multi-frame. But you know where they should be, and so use that in order to detect the correct burst, not just based on threshold. Then you'll be more robust to noise, and that part of the application of the lab, where you actually track the frequency over time, would be more robust. You don't have all these jumps. The other thing is, like, once, let's say, you detect the frequencies, even in the frequency detection part, you can say, well, if I have 5 detection and the variance between them is significant, then maybe I'm not getting a signal. So you can report back, this is I can't figure out what the correction from the burst that you gave me. Okay, so there's a lot of things that you can do to make the application a little bit more robust, which then leads to something. If anybody is interested, I'm posting this frequency challenge. I put a beacon on the 5th floor. It transmits a beacon around 144.280 megahertz. It is GPS discipline oscillator. It means that it's synchronized to the GPS system, and then they have atomic clocks on board. And so it can get an oscillator that's accurate up to 1 part per billion with amazing stability over time, which means that the frequency that I'm generating is accurate to about 1 over 1.5 over 1,000 hertz. Okay, so it's really accurate frequency that it's generating. I'm transmitting my call sign in Morse code 5 times in 2-minute break. And it's doing this continuously. It's not transmitting a really high power. It's only 40 milliwatts, so 16 dBm. But you have a chance then to use your SDRs to track the drift and then intermittently acquire maybe data at that frequency, so switch between them, and then be able to maybe figure out pretty accurately what is this frequency. And I'm going to have you, for those who want to participate, you can submit the frequency on B courses by Thursday, April 7th. And the one that would be the closest will win a radio. Okay? If you already have a radio, we'll figure out something special. Okay? So I think this should be fun. Give it a shot if you're interested. Outside of the building, you're probably not going to have so much coverage. It's not transmitting at really high power. Okay? No cheating. Means that use your RTL SDR, not some other, super frequency reference GPS thing that you can find in a department. Okay? So none of that. And when you submit, please submit how you did it. Okay? So that's another thing that's important. The other thing is radios. Again, who already got the radios? Let's who hasn't gotten the radios yet? Okay, so come tomorrow for. You can come at 6:30 tonight. I'm going to give radios for the EE128 class. So it's Corey 400 as opposed to the Corey 521 because we lost that room. The class should have been ended by now. But one last time. So it's going to be in Corey 400, and you can come and pick up a radio there too. Or tomorrow at the Lab Bash. What else? Some instructions about how to use the radios, what not to do with the radios, what is the band plan that is programmed on them. You can look at the class website. There's a lot of information there. Please go take a look and read them. It tells you also practice of how to use them. Today, John is going to replace my office hours. Unfortunately, I have to be in a meeting exactly at that time. So that's pretty much it. John, anything else? Any questions? Midterm on.
Yeah, I made office hours tonight at 7. Is there anyone planning on going to that? Not, then I'm not going to hold it since I've made it. One person is coming, I'll hold it. If no one is coming, I'm going to go home. So think about that. Okay, by 7:10.
Okay. All right. Okay, so what I'd like to talk about today is, so far, everything that we talked about was mostly linear, right? We talked about linear filtering, we talked about sampling, and sampling of band-limited signals. Okay. So let's say I have a signal, and it's a time signal, and that signal can be anything. And the question is, what is the rate that you need to sample that signal at in order to be able to capture all its information? It could be anything. It could be noise. But I want to reconstruct the noise. Is there a rate? Oh, really, right? Okay, well, let's say eventually it's going to be band limited, okay? Because physical signals are usually are. What is the rate then? So if I have the fastest A to D in the world, what I would do probably is put a low-pass filter before the A to D, and that low-pass filter would be at a certain cutoff, and then I would sample at twice that rate, okay, which is the Nyquist rate, and then I'll be able to reconstruct it. Okay, so if I have a signal that I know nothing about, except that it's band limited, then I would need to use the Nyquist rate in order to be reconstructing it. That means that if I have a band limited noise, I could also reconstruct it. That's great. Fantastic. So that's anything. So I would say at least the Nyquist rate, okay, if you can. And so here comes the question. Okay, so what if I don't want to, I'm not interested in anything, but I'm interested in something? Okay. Something is not anything. What would be then the question is like, what is the rate that I need to sample at in order to reconstruct that signal? Well, it depends. So maybe less than Nyquist. Maybe if I have something that is something but not anything, maybe I can do something better. Maybe I can use that fact. And in fact, you can probably think of a situation where you've got yourself not only a band-limited signal, but a signal which is band-pass. Okay, so yeah, it's high frequency, but it's just narrow band. and that's it. There's nothing else everywhere, right? So you can reduce the rate quite significantly, let it alias, but then you'll still be able to reconstruct it. Okay? So the answer, yes, is absolutely. Maybe we can do something less than this Nyquist rate, because we're trying to sample something as opposed to anything. And I mean, if you think about our world, for example, I look at this classroom. This classroom doesn't look like noise. Okay, if I take a picture of this, reminds me. If I take now a picture of the classroom, I can distinguish between that and noise, right? It doesn't look the same. If I go outside and I look at the skies, you know that's something, right? When I talk to you, it doesn't sound like shh, right? So it is something, and the question is, maybe I can exploit that. And the truth is that people have been exploiting the fact that we're doing something, we're capturing something as opposed to anything, all the time. Here's an example. Do you give me an example, actually? How can you exploit that something is something as opposed to anything? Take a picture with your camera. What the camera does with it. Does it store all the pixels on the flash drive? No, it doesn't. What does it do? It's what? Compresses it, right? Do you listen to MP3s? Yeah, or you listen to, who listen to uncompressed audio here? Yeah, whatever. Audio files. It's good that we have audio files in the world. And one of the reasons that it's good to have audio files in the world is because then companies have the incentive to make really good hardware for cheap that we can use for something else. Right. This is kind of my take of the world. So you can buy like 192 kilohertz sampling rate, 24-bit analog to digital converter sound card, and the opposite digital to analog converter, which, I mean, even a dog would not be able to make the difference. But we can use this to buy it and use it for example, software-defined radios, okay, for cheap. Okay, so yes, anything or most of the things that we do today are being compressed in some form, okay, and stored. Even like when you transfer something over the internet, often it is compressed in some form because it is something as opposed to anything. And the way that people look about compression, for example, in images, you have a camera captures the scene, it has a picture, then the camera processor would compute some compression algorithm that will take this data, exploit the structure in that image, the fact that it's not anything, but actually image have a particular statistics, they have particular structure, and then we'll represent it in fewer number of bits. Now this part could be lossless, but it could also be lossy, in the sense that you won't be able to reconstruct exactly what the values are, but there will be no visual ability, like you would not be able to visually distinguish between them. So you exploit some of the human visual system in order to be able to store this image without losing image quality. And we do that with audio. When you use MP3, it's lossy compression. You don't get exactly back your samples, but you get the information. And you cannot distinguish between, or most of us, cannot distinguish between the non-compressed and the compressed version. Okay. Actually, in medical imaging, we do the same thing. We put a person, this is my area, put a person in the scanner, we acquire all the data, reconstruct images, then we can take those images again and compress them. And so the question that arises here is, it's quite simple. I acquire all this data, I reconstruct an image, I spent a lot of time, maybe sometimes I spend a lot of effort collecting all this data, and then I go and throw most of it away. So I compute something and throw most of it away. And the question that arises is, okay, so if I can do this, why can't I just do that? Why can't I sense the compressed information directly by making fewer measurements? And because I know that the image, in this case, is compressible, maybe I can take this data and reconstruct an image from it. So do the compression in the sampling as opposed to sample everything and then perform the compression. Well, somebody might say, well, maybe you don't have enough representation in this. Maybe you can't do that. And obviously, because we're here, there are situations where this is actually possible. And when I'm talking about signals, it doesn't have to be images. It could be, for example, videos. It could be multidimensional signals that change over time. See? So I can capture this in a compressed way and be able to reconstruct it. So this is kind of the idea, and this is what we're going to talk about today. So here's just a simple example. I just forgot to connect this. So here's an example of audio. Okay, so this is a piece of audio by Pink Floyd. If you look at raw audio, 44.1 kilohertz sampling rate, 16-bit accuracy, and also stereo, non-compressed version will take about 1378 kilobits per second. Okay, that's a lot. If you look at MP3, 44 kilohertz, 16-bit audio, stereo, you can actually play it at least I cannot hear the difference, at 128 kilobits per second. I would argue that even audio files at 256 kilobits per second really can't hear the difference, but some people can. This is about 10.7 or 11-fold reduction in the amount of data that you store. Okay, so it's a one-dimensional signal, and you can reduce its size by a significant amount just because you exploit certain redundancies in audio. The audio doesn't behave like noise. It has certain statistics. Okay? What about images? Images are more complex, right? They're two-dimensional features. Are they more compressible or less compressible? Does it? As it turns out, while the dimensionality increases, the amount of information in images doesn't increase as fast. So in general, as you go for more dimension, while the dimensions increase, the dimensionality of the space increases significantly, the amount of information often doesn't increase as fast. If you think about this, if you look at images, raw images, RGB, 24 bits per pixel, JPEG, an image 1280 by 960, normal compression, you can get down to 1.1 bits per pixel in terms of compression. So now it's a factor of 20 or 22. So even though you not double, but like power, right? Increase the size of your dimension by a power of 2, you can still compress more. Okay, so this is because images have not just redundancy along one dimension, they actually have redundancy in more than one, in 2 dimensions. If you look at, for example, areas which are pretty much flat, right? Which doesn't have there's a lot of spatial correlation that we can use and exploit in order to perform this compression. Okay. Now, what about videos?
From viewers like you. Thank you.
Yeah. Okay, so raw video, and it's a small, actually. This is small size. Now, today, we're doing like 4K video, right? This is raw video, 480 by 360 in terms of size, 24 bits per pixel, 24 frames a second, plus 44.1 kilohertz audio, times 16 bits, times 2 because you have 2 channels. This is about 100,000 kilobits per second. And this is a small video. Okay? So huge amount of data now we store. We have to store the audio, we have to store the 2-dimensional video, and so on and so forth. If you look at MPEG-4, I can store it at 1,300 kilobits per second. Okay, this is a 75 times reduction, and today even you can do way more, even at much much higher resolution video. You can reduce it up to 200 or 300 fold. So huge saving because we increase the dimensionality, but the signal degrees of freedom do not increase as fast. There's a lot of, especially in video, if I would take in a video of this class, I only need to store like this laughter that you just have right now. This may be a person coming in, but otherwise it will be pretty static, right? Maybe my voice. Yeah.
Is compression really only possible because most of the lower frequency components, like you said, there's a lot of flat areas? If you had a video that had, an audio file that had a lot of changes in it, and you had the video had a lot of different colors and
yeah, if the video, like if you ever look at a video, and the problem is that now what I'm going to tell you is going to ruin yourself the whole experience of watching TV, okay, or DVDs or Blu-ray at home. So are you? Let me know if you want to do this or not, because it's really going to ruin it for you. You're just going to be seeing artifacts all the time then, that you would naturally ignore them. Should I go on? Okay, you pragmatic engineers. That's nice. It's like we want to know how the world works. Okay, so if you think of what's going on in a scene, like if you have an action scene, things are moving, sometimes the quality is actually reduced. And the quality would often be reduced in areas that are static. So if you have an active scene, look at areas which are more black or flat. You'll start seeing squares. You've seen that before. Yeah. Some people don't because they focus on where the dynamics is, and that's to exploit basically, the psychoacoustic model of human attention. That you focus on where things are changing. And there you allocate in more bits because this is more important. And so algorithms that do video compression exploit that. So you allocate more bits for this. This is for a constant rate type of video compression. There's variable rate video compression where you can add, more, as the scene changes, you can actually change the rate, increase it, decrease it. But then the problem there, of course, is if you want to stream it, this doesn't work as well. Okay? So yes, absolutely. Okay. So this is the reality that signals have lots of redundancy in them. Useful signals. And so what we can do is we can reduce the amount of information by exploiting the structure redundancy within these multidimensional signals and be able to store them. And that changed the whole industry, if you think about it, from the audio, video industry, now streaming. The thing that you can do now on your phone, all voice conversation, all of this, nothing could have been done without compression. And you use that without even thinking, right? Everybody just saves JPEG. Cameras compute JPEG. It used to be that saving JPEG, you had to buy a card, like a PC card, that would be able to do that in a reasonable amount of time. Okay? There were companies that making these cards to save JPEG pictures. A long time ago. But now, it's unbelievable. So how does compression work? So there's many ways to do compression, but this is the kind of a cookie cutter example of how things are being done. You've got your signal. What you do then is you often transform it into some other domain. So you apply some mathematical operation on it such that the signal becomes more sparse or concentrated in different coefficients. Here's an example. Example for this are the discrete cosine transform. If you have audio has more low frequencies than high frequencies. That's the case. Then the discrete cosine transform will have more coefficients, large coefficients in the low part frequencies, and then fewer in the high frequencies. If you remember, we talked about the wavelet transform. That's another transformation that allows you to represent signals in a sparser way. And of course, that's going to depend on the type of signals that you have. After you apply this transformation, that is often non-destructive. Okay, so the transformation is not something that it's not lossy. That's not the lossy part. The lossy part comes in the quantization. You take the coefficients of the sparse transform and then you quantize them. And the quantization is often done according to some psychoacoustic model, if we're talking about audio. So you quantize certain frequencies, you quantize depending, so for example, according to our the way that human hearing is done, if you have a certain tone at a particular frequency band, it's going to attenuate, you won't be able to hear within that certain band other tones. So it's going to mask other tones. And you kind of, you listen to, maybe podcast music or whatever on the train, and then suddenly, there's lots of noise, you can't really hear what's going on. Okay? That often happens, right? You have a phone conversation, somebody else speaks, you can't really hear anything. Right, you have to kind of put and the reason is because of this masking. Okay? While you do hear it, the brain cannot interpret it. Okay? So there are models that people have developed, and you quantize based on this, both visually, also auditory. Yeah.
Does this have anything to do with frequency integrity?
Not necessarily, no. This is the way our sensors work. After you quantize, what you do then, now you've got a lot of redundancy because now things are broken into pieces. And so now what you do is what's called an entropy encoding. So you exploit some statistics in order to store the data. Here's an example. Let's say I computed some transformation that makes my signal sparse. Now I have but what do I mean by sparse? Usually there's large coefficients. There's a lot of really small ones. Then I do quantization, all the small ones go to 0. And now I can do, for example, run length encoding. So whatever is 0, I have a bunch of 20 zeros, one after the other, I can store them as 20 zeros, as opposed to 20 zeros. Okay, so this is one example, but there's more sophisticated type of entropy encoding. So for MP3, you've got the discrete cosine transform used for compression. For JPEG, it's also DCT, but it's DCT that's broken into 8x8 blocks. For MP3, I think it's 512 blocks or 256 blocks. I can't remember exactly the details. But JPEG will take 8x8 blocks and will compute a discrete cosine transform on them. Discrete cosine transform is kind of like the DFT, but instead of using complex exponential, it uses just a cosine. Okay? So it is still an orthogonal transform. JPEG 2000, which is a more modern type of compression, which really didn't pick up, uses wavelets. But wavelets has snuck to videos, and especially for streaming videos. They often use wavelet type of compression. And then if you look at videos, it's often MPEG. MPEG uses DCT and some time differences. So you look at time differences between frames, and then you do DCT over that. Okay. So and then there's other forms. For example, if you can compute kind of motion vectors. So if you have two frames, you try to find some correlation between nearby pixels. So if you have a frame that moved, then you just find what is the motion vector at each position, and then after applying the motion vector, you compute the difference. So that gives you more compression if you got the motion vectors right. If you didn't get them right, then you don't have as good of a compression. And of course, you have to store the motion vectors. So there's always a trade-off of all these things. Any questions? One of the things that in the preferred project you probably would like to do is perform some sort of compression. So the tool sets that you'll have are, for example, DCT, FFT, DFT, wavelet, hard, Dolbesch wavelet, whatever you pick, and then you can perform quantization and so on and so forth. And you'll be able to see how well this is actually performing. It's not really hard to do. To do really, really good compression, you have to be very careful. But to do an okay compression, you can do quite well with very basic tools. Okay, so here's an example. Here's the sparse transformation for audio. This is a piece of audio. You compute DCT of over, I think, 512. And then you can see that there's a lot of low frequency components, but then the rest are zeros. Now, I have to say that I took an already MP3'd, right? So it's been quantized such that it actually looks like that. So, but that's, it kind of makes sense. So this is a sparse transform part. For images, here's an example of taking this image, breaking it into 8x8 blocks, and computing on 8x8 blocks a discrete cosine transform. And pay attention is that all the flat part will have basically one coefficient in the DCT, which is really the average. If it's flat, then an 8x8 block could be represented by just one pixel. What is the average of that block? In places where you've got yourself an edge, then you see more and more coefficients. Here you see more coefficient, here you see more coefficient, here you see more coefficient. Wherever you have structure, like this one, you see more coefficients. Eyes, you see more coefficients. Okay. Now if I take all the coefficients of this image and sort them by intensity, and I take all these coefficients and sort them by intensity, the blue line here is the intensity of sorted pixels here, and the red one is sorted here. And you'll see that this drops significantly fast. This is log scale. Right? This is log scale. So this drops significantly fast. Here's a factor of 100 less in terms of intensity. So that means that probably I could have cut here and be able to reconstruct an image which is really good quality by throwing all these away. Okay? That's what compression really means. So sparse transformation, really what it does is when you sort in the coefficient, you'll see a significant drop in the values of these coefficients. Often it's not going to be 0, okay, because these are real signals that have noise in them. Noise is not compressible. In fact, this is one way of removing noise, is to compute a sparse transformation and then threshold. We'll get to that. Okay, so here's the 1D signal. What would you do to make it sparse? What? Hard transform would be a good one. Yeah, that's a good one. Any other ideas? Yeah, like time difference, which is really just the hard transform mother wavelet, right? So taking the finite differences really is the detail coefficients of the hard transform. And then if you do that, you can maybe just need to store the DC component of this, and then you get yourself a compression. And if you do that, if you look at finite differences, you see, yes, the signal is really sparse. All the information is really just in the changes, in the edges. There's no information anywhere else. Hence, I don't care what's going on here. Why should I store this value? I don't need to store this value. All the information is in these jumps, these bumps. Okay, so this is compression and sparsity, but how does it help us to do compressive sampling? So it's all about this sparsity and compressibility. And I want to talk about a very important concept, which is sparsity versus noise. Okay? So sparse. What is sparse? Would you say that this signal is sparse? Yeah, looks sparse. Has 3 coefficients. Actually looks like an NMR spectrum. And just to push in a little bit of this nuclear magnetic resonance stuff to you. Okay. What about this angio? This angiogram of a hand. You see blood vessels. You don't see much else. This is contrast injected into your blood vessels, and so those are the dominant signals. And so there's no much other tissue that shows up here. Okay, so I would say these are sparse. So what is maximally not sparse? Noise. I mean, it doesn't have to be white. I would say noise is absolutely not sparse. Noise is not sparse because it's everywhere. It's always everywhere. Touches everything. Changes everything. No matter what I do, I compute a Fourier transform, noise stays noise. Okay, so noise is really maximally not sparse. And the one thing that is really useful when thinking about sparse signals is that when you've got sparse signals, it's really easy to separate between signal and noise. Because if I look at a noisy image, I can't come up with a really good vacuum cleaner that, will pull out the noise, but then will not also pull out the details. But when I've got a sparse signal, then when I hit something that's really large, I would say, well, you probably are some signal. Maybe you're a little bit noisy, but probably your signal is much larger than the noise. I'll keep you. And whatever is small, I'm just going to, vacuum clean it. And when you've got the sparse signal, it makes it super easy to separate between most of the noise, not all of it, of course, because even the sparse coefficients do suffer from noise. But I can separate between most of the noise and the signal just by setting a threshold. It's a very simple operation. Just setting a threshold would then pick up the signal coefficients and then give you the signal that you have while removing lots of this noise. Yeah, let's get out of here. So the point is really that sparsity really makes it simple to separate. Now that leads us to what we talked about before. What is really, not all our signals are sparse. But you can make them sparse if you know their statistics. You know how they behave. And here's an example. This object is called a Shep-Logan phantom, often used to simulate data in computed tomography and other fields. It's not sparse. But it's piecewise constant, hence it has sparse edges. If this was noisy, I can compute the edges, and now I can perform denoising effectively. What about other images, like brain images, for example? I showed you, I think, this before. If you can take a brain image and you compute the wavelet transform, and these are, if you remember from HAR wavelet that we talked about, there was the detail coefficient and there's the approximation. Then we break these into detail and approximation, break these. When you've got images, then you've got detail coefficients in 2 dimensions. Okay, so these are mostly filters that represent edges that are horizontal. These represent edges that are, or high-frequency information in the vertical direction, and these represent high-frequency information in the diagonal direction. Where these are, again, broken into different scales and scales and scales. So these are high-frequency, basically bandpass filters. These are lower frequencies. And then you break them on and on and on. Now, if you stare at this long enough, you see this is noisy, but now signal pops out of the noise. And if you then denoise it by performing a threshold, and actually in this case I did not do what's called a hard threshold, I did what's called a soft threshold. And a soft threshold is slightly different. What a soft threshold does is below a certain value it actually thresholds, but beyond that it shrinks the coefficients. Okay? So really large coefficients are not affected much. Small coefficients are shrunk a little bit more to a point where you completely remove the signal. And if you think of this lookup table as a threshold, right? This lookup table is a threshold. Whatever is above returns exactly the same. So it's linear above a certain threshold and 0 afterwards. A soft threshold is this lookup table. You put an input, and that's the output. For a hard threshold, you put an input, that's the output. You put an input, that's the output. That's a hard threshold. Soft threshold is you put an input, that's the output. Turns out this is a little bit more robust to spurious type of results. But this is the result, and when I reconstruct back my image, I got myself a denoised version, which is quite extraordinary. Like it preserves all the structures, high resolution frequency stuff. Things are being preserved very nicely. All the edges are nicely depicted, but noise is just being vacuum cleaned. It's a form of adaptive filtering just by performing this transformation and then putting a threshold. It's definitely nonlinear. Okay, it's nonlinear. I put a threshold. It's nonlinear. Then you don't have to think of other things. Here's an example of a cardiac. Cardiac scan, if you look at a cross-section, you see that's quasi-periodic. Quasi-periodic means that over time, if I compute the temporal frequency, it's going to be sparse. I can use that to perform denoising. I can use that to perform compression. I can use that to do many, many things. Now, how does this relate it to compression? Because in compression, you really only need to store is the zeros. Or effectively, when you quantize, most of the signal will become 0, and the other coefficients will be broken into parts. So they'll deviate from those values. So you're introducing some error, but that error hopefully is not significant. But it can also remove noise. So noise removal and compression come hand in hand, because if you have something that's really noisy, of course it's not compressible. So here's an example again of a brain with the wavelet coefficients. The more coefficients I add, the more accurate my representation of this brain is. And I only need to stop at about 5% of the number of coefficients, and it's barely possible to distinguish between the differences. Okay? This is pretty cool. But really, I didn't say anything about compressive sampling. I only talked about the compression part, the analysis part. I could do that. If I have a signal, I could do that. It doesn't say anything about the sampling component. So how do we go from this concept to compressive sampling? And we're going to continue next time, but I'm just going to give you kind of a hint. So instead of thinking about making samples of the signal directly, we're going to start thinking about making measurements of the signal, but measurements that not necessarily samples the signal directly. Maybe they sample some transformation of that signal or some other representation of that signal. So if you look at the Shannon-Nyquist sampling, it's really the worst case. It's the worst case scenario. I mean, Shannon, like serious guy, right? Nyquist really, really uptight. Like has this tie, it's like you don't want to mess with it. They took the worst case scenario. Whatever was within a band, you'll be able to reconstruct. Worst case. With compressive sampling, the results are slightly different. The results in this area are that sparse signal statistics can be recovered from a small number of non-adaptive linear measurements. And it's linear measurements rather than just making samples. And this is something that we'll get to this. So really what it does, it integrates the sensing, the compression, and the processing all within the same framework. So if I make compressive samples, effectively I perform compression. And the idea of making an images out of these samples is a reconstruction. It's also decompression. It encompasses all of these together. And this is based on other concepts of what's called incoherency between the signal and the measurements. And what does it even mean, incoherency? And this is what we're going to go and talk about on Friday. In what situation it is possible to perform this type of a compression. And just to kind of give you a hint, let's say there are only 4 students here. And I want to get a picture of this classroom. Okay? So the picture of this classroom would be, students are sitting here, here, and here. Right? If I go ahead and I try to sample one by one, right? Like in order to figure out where students are, I have to go like one seat by seat. If you think about taking a camera, each pixel on a seat, and see whether it's occupied or not. If I'm going to skip signals, if I'm going to skip seats, am I going to be able to reconstruct my signal? There's just no way. There's no way I will be able to do this, okay? So it's not magic. There's just no way whatsoever I'll be able to recover who's sitting here if I sparsely sample a sparse signal. That's not going to happen. So something else needs to be happening. Okay? And that's what we're going to talk about next time. Okay? So if you want your radios, come tonight or tomorrow. And that's it. See you on Wednesday. Friday. Okay. You want to do it now, quickly?
Yeah, we can do it now. Are you
For the ham radio first, if you just hand out the radio,
I'm going to hand the radio. I'm going to show you some stuff, like discuss a little bit of how to operate them, maybe how to program them, how to create a cable, and then maybe we'll do a net over. Like we'll give you the radio, then we're going to leave, and then we'll continue on doing like a net on a repeater.
I already got my radio.